Okay, last lesson of this school year, last lesson before workshop in the summer, we are going to talk about bond polarity and molecule polarity. Now, this is a complicated lesson and it's always difficult that we do it at the end of the school year. So I want you to learn as best as you can through this notes and then other two things I'm going to post, a homework and a tutorial. Do it as best as you can, and then know that at least one of the days of workshop will be dedicated in practicing this and to make sure that you fully understand it before going into AP chemistry. But also call me on Zoom if you are confused. Okay, so there are two kinds of covalent bonds. Remember, a covalent bond is a bond where the electrons are shared instead of transferred, and there are two different kinds. A polar covalent bond is a bond where electrons are shared unequally. So one of the atoms is going to have a greater pull on those electrons than the other, and so they will spend more time closer to the one atom than the other. They're not shared equally. Whereas a nonpolar covalent bond is a bond where electrons are shared equally. Okay, so neither atom has a stronger pull on the electrons than the other, and they'll spend their time sort of spread between the two of them evenly. Now, dipolar is another word for a polar bond where the electrons are shared unequally, and then dipole is another name for a polar molecule. A polar molecule will be one in which the polarity of the bonds contributes to an overall, sometimes called a dipole moment, where there's a general pull in the molecule. So we're going to start with bonds. In order to determine whether a bond is polar or nonpolar, we are going to look at a chart that is here. I'm going to show it to you on my computer. So if you have not opened that, go ahead and open that on your computer. That's in the same assignment there. This document is shared, and it's got that chart there that's called the chart of electronegativities. Electronegativity is the attractiveness of the nucleus for electrons in a shared pair of electrons, let's say in a bond. So you've got a bond going on. How attractive is the nucleus of the atom to the electrons in the bond? Because the more attractive you are, the more likely the electrons want to spend time by you. If the two atoms are equally attractive, they'll get this nonpolar covalent bond. If one is way more attractive than the other, you get this polar covalent bond where they're shared unequally. So to compare that, we're going to look at our chart, and for our electronegativity chart, we see that fluorine has the number 4.0 in the electronegativity chart, and boron has the number 2.0. So then to figure out delta En, which is the difference in electronegativity, for this we always take larger minus smaller, so we do 4 minus 2 is 2.0. 2.0 is the difference in electronegativity there. B is 2.0, Cl is 3.0, so delta En for that bond would be 3 minus 2, or 1.0. Now, if your difference in electronegativity is less than 0.5, then we consider that to be a nonpolar bond. So because that means they're sharing fairly equally, and so the electrons will spend their time fairly equally between the nucleuses. If delta En is greater than or equal to 0.5 or less than or equal to 2.0, we will consider that a polar bond. A polar bond where the electrons are shared unequally, and they will spend more time on one atom than the other. So they're more attracted to one atom than the other. If delta En is greater than 2, that's when you end up getting the ionic bonds. You end up getting transfer because the one is not pulling hard enough to keep the electron, so the other one just takes it. Okay, but we're going to focus mostly on nonpolar and polar bonds right now and ignore the ionic compounds for now. Okay, so then now we've got this, and so we know that, notice that both of these are polar bonds, so these are both polar bonds, and then now they want us to indicate which one is a negative pole and which one is a positive pole. So for BF, the negative pole will be the one that's more electronegative, and the positive pole, the one that's less electronegative. For BCl, the chlorine is more electronegative, gets the negative, less electronegative gets the positive. Now let's do silicon dioxide, or silicon oxide. So delta En, we look at silicon. Silicon is 1.8, oxygen is 3.5. So we start with the larger one, 3.5 minus 1.8 equals 1.7. And then the other one, PP, P is 2.1, but they're both 2.1, so 2.1 minus 2.1 is 0. So this one is nonpolar, but this one's polar. So there isn't a positive or negative end on the PP, but on the SiO, the O is the negative end, and the Si is the positive end because the O is more electronegative. Now here we have a double bond. That's okay, you can have double bonds. The process is still the same. Double, single, triple, you always do the same thing. So delta En for the first one, O is bigger than C, so O is still 3.5, C is 2.5, so you get a difference in electronegativity of 1. C to S, S is 2.5. And C 2.5, so you get a difference in electronegativity of 0. So this one is nonpolar, this one is polar, and in the C to O bond, the O is the minus and the C is the plus. Okay, so you turn the page. Why don't you pause it and try these three, see if you can predict correctly whether they're going to be polar or nonpolar bonds, and then come back in and see what I did. So this will be 4 and 2.1, so delta En here is 1.9, and this one is 2.1 and 2.5, so delta En here is 0.3, so this one is nonpolar, this one is polar, and in the HF bond, the minus goes to the F, and the positive goes to the H. C is 2.5, B is 2.0, 2.0, 4.0. So the difference here is 2.0, the difference here is 0.5. So both are considered polar, but this one just barely, whereas this one very polar. So in the BC bond, C is the minus and B is the plus, and in the BF bond, F is the minus and B is the plus. Okay, now we're going to do CSI and CS. So CS is 2.5 and 2.5, so that one's 0. C to SI is 2.5 and 2.1, so this is 0.4. So both of these are considered nonpolar covalent. Nonpolar covalent. Okay, so that's the simpler part, figuring out the bond polarity. On the next video, I'm going to go into molecular polarity.